Well, my title is Assessing Fine-Tunings in Physics, but I had a subtitle, How Many, How Fine, and How Come. And of course, how many refers to the number of fine-tunings there are. How fine refers to the precision required for the fine-tuning, because when we want to determine whether these fine-tunings really are significant or just a coincidence, it all depends on that. But then perhaps the most interesting question is how come? In other words, what is the explanation for these fine-tunings? I don't think that works unless there's a... And actually, although in a way that's the most interesting question, I'm not going to focus on it too much at the moment. Oh, I see, it has to get... No, I'll do it by hand. But let me just say right at the beginning that broadly speaking, the three sort of explanations to think about are the multiverse, which is very popular in some courses, though not in others. More philosophical is the idea that in some sense consciousness collapses the quantum wave function, and we need to have consciousness therefore in order for the universe to come into existence. This is a famous picture by Wheeler. The universe starts with a big bang, develops consciousness, which then reflects back on the Big Bang and forms a sort of closed circuit, and the universe comes into being. Because I should stress that these fine-tunings are supposed to be connected with the existence of observers in some vague sense. And then, of course, the third explanation is that, or maybe it just reflects the fact that some creator chose the constants of nature very kindly so that we would come to be. And these are three different types of explanation. In some sense, that's perhaps a scientific explanation, that is perhaps a philosophical explanation, and that is perhaps a theological explanation. Well, I'm not going to get really too much into that. I'm mainly going to focus on the question of the fine-tunings themselves, because that in some sense is part of the motivation for all of these bizarre speculations about the multiverse. I should say people don't only propose the multiverse because of the fine-tunings, but historically the fine-tunings are perhaps the original motivation for proposing a multiverse. So I will focus mainly on the fine-tunings because that is the title of the workshop today. And furthermore, I'm going to focus more on the physics than the philosophical issues. Now, but for historical and nostalgic reasons, I can't but help reflect back on the fact that I was also involved in a Templeton-funded project, and that went back to the 2000. Templeton had a program called Cosmology and Fine-Tuning, and myself and Robert Crittenden and Martin Rees and the author, we got a grant, I guess rather like yours, for a project called Fundamental Physics and the Problem of Our Existence. And I really just wanted to mention this just to encourage you, because we had three conferences. One was in Cambridge, the first one in 2001, Anthropic Arguments in Fundamental Physics and Cosmology. There was then a meeting in Stanford in 2003 called Universe or Multiverse. And then there was a meeting in Cambridge in 2005, 10 years ago, called Expectations of a Final Theory. So we had three meetings, and what came out of those meetings, in fact, was a book. It's the book I edited called Universe or Multiverse, which I like to think is one of the classic works in the field because it looks at the multiverse from all points of view. It's got contributions from cosmologists, particle physicists, philosophers, and it includes people who believe it and people who don't believe it, because I'm sure you realize the multiverse is a very controversial issue, which is why there's a question mark. Probably the most important part of the title is the question mark. And there is the, just again for nostalgic reason, here is the picture of the meeting in 2001, which took place in Martin Rees's back garden, well, in the house. And I'm sure you can recognize the various people there. George is there. Sorry, it's a pity that pointer doesn't work, but George is there, and I am there, and various other people. And part of the point of this picture, though, is to emphasize how many, well-known cosmologists really, and physicists really do work on this subject. Because there's, in the last, I've been interested in this subject really for about 40 years, I think. But the point is that in the old days, talk about the anthropic fine-tunings and multiverses was regarded as very bizarre and heretical and almost taboo. The word anthropic, would be enough to get many people in a rage. But now, it's actually respectable in the sense that there are many respectable physicists who talk about it and write papers about it. It doesn't mean it's not controversial, but the balance of opinion has changed. And in fact, there's a nice quote from Frank Wilczek, who attended the first and the third meeting. And this was Frank speaking in the third meeting. The previous gathering had a defensive area, prominently featured a number of physicists who subsisted on the fringes, voices in the wilderness who had for many years promoted strange arguments about conspiracies among fundamental constants and alternative universes. Their concerns and approaches seemed totally alien to the consensus vanguard of theoretical physics, which was busy successfully constructing a unique, mathematically perfect universe. Now, that means in 2005, the vanguard has marched off to join the prophets in the wilderness. And so there really was actually, I said there's been a change since myself and Martin Rees wrote our paper on the subject in 1979, but actually even in the period between 2001 and 2005, there was quite a big change of opinion, because the funny thing in science is really what is regarded as respectable is really just determined by a few influential people, and you just need a few people Stephen Hawking and Wilczek and Weinberg talking about this, and people think, oh, well, it must be respectable after all. It doesn't mean they're right, but it's a sociological phenomenon. It always interests me, because we're talking a bit about the sociology of science here. There are these taboo words. Anthropic, as I said, the A word is a taboo word. 20 years ago, it was dangerous even to use the word. You'd say the A word. They're still taboo topics, which consciousness, for example, is taboo in some quarters, but less taboo now. And of course, the most taboo word of all, perhaps, is God. If you're talking to a science audience, a physicist audience. Now, I want to start off with my favorite diagram. Some of you will have seen this before. But this sort of is the Ouroboros, the snake which is swallowing its own tail. And around the body of the snake, we have the various structures which exist in the universe. So at the bottom, we have people. And then as you go to the right, you get bigger things like mountains and planets and suns and solar systems and galaxies in the universe. And on the left, we get progressively smaller things like ants, amoebas, DNA, atoms, nuclei, and elementary particles. So as you go around in a clockwise directions, the scale is decreasing. You can see the scale going from roughly, it goes from roughly 10 to the plus 30 to 10 to the minus 30 centimeters as you go around the body of the snake. So the body of the snake is rather like it's like a ruler in which every minute corresponds. It's like a clock where every minute corresponds to the Decada scale. And I like to use this diagram to just summarize in 1 minute the history of physics. Because you see, the history of physics, in a way, consists of expanding our awareness outwards to ever larger scale and inwards to ever smaller scales. And so let's just quickly retrace. You all know the history, but let's quickly retrace the history. So our concepts of the universe have changed. So if we go on the outward journey, we started off with our geocentric view of the world. Then, of course, Copernicus came along and we had the heliocentric view of the world. And then we realized that our sun is just one of 100 billion suns which forms the galaxy, and then we thought the galaxy was the center of the world. We thought the galaxy essentially was the world, was the universe. And nowadays, most people have the concentric view, cosmocentric view. In other words, we can see to the edge of the universe, the distance light has travelled from the Big Bang. And the cosmocentric view says that is the universe. And so the outward journey has meant we sort of shifted our concept of what is the universe, how big it is. And of course, if you take this to its logical conclusion or illogical conclusion, you come up with the idea of the universe, the multiverse, the idea that there are actually, our visible universe is part of a bubble, which is one of many, many other bubbles. And then if we go on the inward journey, we of course discovered atoms, and we also discovered the forces of nature, and those forces of nature linked the macro world with the macro world. So for example, the same electric force which holds the electron in orbit around the nucleus is the same force which gives solid objects their structure. We then discovered the strong and the weak forces, and the same forces which hold the nuclei together are also responsible for nuclear burning in the sun. So there's the atomic bomb. Then we have our standard model, and we have the electroweak force. This represents the discovery of the Higgs boson a few years ago. Seems to confirm that model. And then we have supersymmetry, and we haven't yet discovered supersymmetry, but again there's a link there because supersymmetry may be related to the dark matter which we find in the halos of galaxies. And then there's the grand unified theory, which unifies the weak and the electric and the strong forces. And that may be related to the formation of structure, because we know that at early times grand unified effects came in, and that may produce the density fluctuations and inflation and things like that. And then of course right at the top we come to M theory, which is also obviously highly speculative. But to me that diagram represents the triumph of physics in explaining not only all the different structures that exist in the world, but also the links between them, the links between the micro and the macroscopic sides of the Ouroboros. So this is why this is my favorite diagram. And of course the culmination of this is the Big Bang. And the reason the head swallows the tail is because, of course, when you look the greatest distances, you're looking back in time to when the universe was very, very small, and when you go back to the Big Bang, of course, it's very small. And so the very large becomes the very small, and so that's the significance of that. But you see, although, and what's striking is that we've almost already got to the top of the Ouroboros, so we've almost discovered everything. That's why you might say we're close to a theory of everything. So it's a triumph of physics. But it also poses a bit of a dilemma. And the reason for this, I'm going to highlight this paper, which George will know very well, a paper which appeared in Nature recently. Because the point is, when we talk about M theory in the multiverse, we're talking about things which are, in some sense, not observable or not easily testable. And so it raises the question, when you get to the top of that Ouroboros, what is the nature of science? And of course, in this, I expect George will refer to this. I don't completely agree with George's and Joe's view, but it is a really important issue. And the one thing I definitely agree with was your statement, George, at the end of the paper, that it's important to have meetings to discuss this issue, and I guess this is an example of such a meeting. Now, I want to go back. Really, Roger mentioned I've been working in this for a long time, and actually my first paper on this topic was in 1979 with Martin Rees, and it was a review paper in Nature which sort of wasn't the first paper on the subject, but it had quite an impact, I guess. And I just read the abstract. The basic features of galaxies, stars, planets, and the everyday world are essentially determined by a few microphysical constants and by the effects of gravitation. Many interrelations between different scales that at first sight seem surprising are straightforward consequences of simple physical arguments. not anthropic, simple physical arguments. But several aspects of our universe, some of which seem to be prerequisites for the evolution of any form of life, depend rather delicately on apparent coincidences among the physical constants. And that's the anthropic part of the title. And the point was, we brought all the anthropic arguments together. We had some new ones. But let me just... it's too hard to resolve this, but this was just a demonstration, plotting mass against length, and all the sort of objects that exist in the world, like atoms and galaxies and stars and planets and men, people rather, exploding black holes, can sort of be represented in this diagram. And we showed that all the scales, if you know, in units of the Planck scale or whatever, are determined just in terms of alpha, which is the fine structure constant, and alpha g, which is the gravitational fine structure constant. And that's very, very small, 5 times 10 to the minus 39. And that's just straightforward physics. That diagram doesn't have anything anthropic about it. But it was surprising because it wasn't realized how things were to an order of magnitude determined in this way. But now let's go back to the Ouroboros again. And all these different scales, which I can actually write them in terms of alpha g, because it's alpha g which is actually so crucial. And so in terms of the Planck scale, alpha g is 1. People are about alpha g to the minus 3/4. Stars have got a size of, this is the size, alpha g to the minus 1, and the size of the universe is alpha g to the minus 3/2. And that simply comes from straightforward physics. But you see, the big question is, what determines the value of alpha g? I told you that alpha g is 10 to the minus 40, really very small. Okay, so alpha g is much less than alpha because the gravitational force between two protons is so much less than the electric force. Well, you see, since alpha g is 10 to the minus 40, you can see alpha g to the minus 3/2 is 10 to the minus 60. So that's why this diagram has 60 decades of scale. It's because alpha g is 10 to the minus 40. But you see, although simple physics explains this, it doesn't tell you what the value of alpha g actually is. And so that was the question which myself and Martin were interested in. Why is alpha g so small? You see, you could change alpha g, and all the scales would change, but this Ouroboros would still have exactly the same form. It wouldn't be 60 decades, it might be 40 decades or 100 decades, but the diagram would look the same. Now, and so this raises the issues of tuning. Now, there are many different types of tuning. And so when people talk about tuning, you've got to distinguish between what we mean. For example, I've already explained that simple physics gives these dependencies on alpha g, and that naturally implies that there are relationships between different scales, which you might think were profound, but actually aren't. The simple example, a human being, the size of a human being, is the geometric mean of the size of the universe and the Planck scale. Now, you know that's true. That's why the human beings are at the bottom. And you might think, well, that's rather mystical, isn't it? You know, where the geometric mean. But no, it's straightforward physics. So some apparent coincidences are natural. And the point is, you don't know when you start out which coincidences are going to be natural and which are going to be profound. I mean, it's still interesting, but it's not something you can't explain. Then there are the so-called the selection effects for observers. And this is sometimes called the weak anthropic principle. And I regard this as non-controversial. It says that if we are observing the universe at a particular time, that imposes a selection effect on the conditions of the universe. And the most obvious example of this is Dickey's famous argument for why is the universe as big as it is. And I'm sure you know this argument. Dickey's argument simply says, we can only be around after we waited long enough for the lifetime of a star, okay, because stars produce heavy elements. So we can't arise until we've had stars. And roughly speaking, the lifetime of a main sequence star is something like alpha g to the minus 1 times TP is the proton time scale. On the other hand, if you wait much longer than that, all the stars will have burnt out. You'll have had many generations. So basically speaking, we can only be around when the age of the universe is something like alpha g to the minus 1 times the proton time scale, which is 10 to the 10th years. Obviously, it's very rough. I mean, there are huge orders of magnitude missing here. But the point is, the argument that we can only be here asking questions at roughly 10,000 million years is just logical. Okay? I mean, obviously, you can argue about whether it's 10 to the 9th or 10 to the 11th, but the weak anthropic principle is simply a statement of logic. However, what is much more controversial, and what myself and Martin drew attention to, were the apparent tunings between the constants which are needed for observers, but which aren't predicted apparently by physics or by any obvious selection effect. And that's what's called the strong anthropic principle. Now, people use the strong anthropic principle in different ways. When we used it, we just used it to mean the fact that the constants themselves, this is saying that given the constants exist, there's a selection effect on when and where we observe the universe. This is saying that there's a relationship between the constants themselves. Now, actually, of course, if you believe there's a multiverse, then the strong anthropic principle just becomes a version of the weak anthropic principle, because it says there are lots of universes and therefore we have to be in one which allows us. But of course, the existence of the multiverse, that's only one possible explanation of the fine tunings. And the other thing to bear in mind is that there are actually lots of other fine tunings which are nothing to do with the anthropic. In other words, nothing to do with us. They're to do with particle physics. For example, there's a fine tuning associated with the Higgs mass. There was a nice article by Wilczek where he classifies the various physical parameters. And I'm not going to, it takes too long, and I can say I'm going to not have time for this, but there's a little diagram there which you can follow up. It's in the book, so that's just to whet your appetite. Now, sorry, when I say in the book, I mean the Multiverse book. But the other problem is this. You can write down all the constants of physics. You know, there's only like 30 constants of physics. So some of them are particle physics, some of the strength of forces, some of the cosmological parameters. And the question is, which constants are you actually trying to explain? Which are the fundamental constants? And in fact, how many are they independent? You see, it might be that a final theory of physics wants to relate all of these, in which case you might find there's only one or two, there'll have to be some constant, but there may only be one or two fundamental constants and everything else will be derived. But actually, that's not the situation at present. At present, we don't know what the relationship is between these various constants. They seem to be independent. They seem to be, in other words, there is no actual explanation. So when you talk about the fine tunings, the question is how many are independent? Because some of these fine tunings may end up being a natural prediction of physics. But we don't know in advance because we don't have our final theory. Now, I have to say a little bit about this word anthropic, which is rather unfortunate. Of course, anthropic comes from the Greek word for man. When I say man, I mean humans. And of course, the anthropocentric view says we're at the center of the universe, but of course that went away with Copernicus. So there was the anthropocentric view. And then we had the mechanistic view associated with Isaac Newton, which basically says, you know, the universe is a great machine, and it more or less functions independent of whether we're here observing it. So humans are essentially irrelevant. And that was the view which prevailed for hundreds of years, and indeed still does prevail in many quarters. But the anthropic view is a sort of reaction of that, which comes from physics itself, which says some features of the universe are explained by the requirement that the observers should arise. And I gave you a simple example in Dickey's argument for the age of the universe. But actually, it's a terrible word because it's nothing to do with humans in particular. That makes it sound as though it's anthropocentric again. and I prefer to look at this as a complexity view. The universe is fine-tuned for complexity, so the Big Bang should lead to increasing order and complexity culminating in, if you like, in mind or observers. But to me, the existence of observers may just be a sort of incidental result of the fact that you've got complexity. Most of the anthropic arguments aren't specifically for humans. They're basically saying we need things like chemistry and stars and galaxies and things like that. So that's the way I prefer to look at it. But now let me ask, what are the fine-tunings? Because that, in a sense, is my main purpose. And well, the four forces, you remember the four forces, which were basically those horizontal lines in the Ouroboros. There's the gravitational force, 10 to the minus 40, and the electric force, the fine structure constant, 10 to the minus 2. There's also the weak force and there's the strong force. And I won't define these dimensionless numbers very precisely, but they are dimensionless. That's the key thing. And the question is, will our final theory explain the values? Because at the moment, they don't. There is no explanation for these values. And now what I want to give you are some examples of relationships between those constants which aren't actually explained, but seem to be necessary for life. Now, the first one is to do with stars. Now, the argument's a little bit technical, but I'll just give it to you as simply as I can. Simple physics shows that all stars have got a mass of something like alpha g to the minus 3/2 times the mass of a proton. Now, this is very simplistic because, of course, stars have a range of masses of about a factor of 100. But to an order of magnitude, that's what the twiddle means, they all have alpha g to the minus 3/2 times the proton mass. And that's simple physics. That was one of the points in that first diagram I showed you. But there are two sorts of stars. There's convective stars and radiative stars. And the convective stars, this is referring to the envelopes. And if you've got a convective star, the heat gets out to the surface through convection motion. If you have a radiative star, it comes out simply through radiation. Both types of stars exist in the universe. And the separation is roughly a solar mass. But in fact, you can calculate in terms of the fundamental constants what it is. And it's alpha g to the minus 2 times alpha to the 10th times the proton mass. So that's a prediction again from simple physics. Now, the only reason that that actually lies in the range in which stars actually exist is because of this remarkable coincidence. Alpha g is the 20th power of alpha e. Now that's true because remember alpha e is 10 to the minus 2, so if you take the 20th power you get 10 to the minus 40. But the point is it needs to be true. Now you might say, well, why is that anthropic? Well, the radiative stars are needed for supernovae, because if you have convective motions, you don't end up with the onion skin model of a supernova. And it's thought that the radiative stars, the convective stars, may be associated with planet formation, but I don't have time to get into the details. But that's why that, in some sense, might have anthropic significance. But in any case, what is undoubtedly true is the only reason you have both convective stars and the radiative stars is because of this coincidence. It's my favorite one simply because of the powers involved. So this is required, but it's unexplained by physics. Page has done a more refined calculation. It constrains E, if you like, to 3%. Now let's think about supernovae. Now, supernovae are also necessary for life because they cook the heavy elements through nuclear burning, and when they explode, they get disseminated and get absorbed into eventually us. But the only reason you have a supernova explosion is because alpha G is the 4th power of alpha W. Now, and that comes out of straightforward physics. The argument, roughly speaking, is this. What happens when a star collapses? The neutrinos get generated in the hot core and surge through the envelope of the star, and they blow off the envelope. If the weak interaction was too weak, because the neutrinos are interacting with the envelope through weak interactions. If it was too weak, they would just go straight through the envelope and it wouldn't blow anything off. If the weak interactions were too strong, they would never get outside the core. So that is one of the conditions. Alpha G is the fourth power of alpha W, which is true because the fourth power of 10 to the minus 10 is 10 to the minus 40. But again, it's unexplained. In fact, this same coincidence also explains why we get an interesting amount of helium being made through nuclear synthesis in the Big Bang. You would either get 100% helium or you'd either get 100% hydrogen or 0% hydrogen if it wasn't for that coincidence. It's also, oddly enough, related to why the baryonic and dark matter densities are comparable if the dark matter is made of WIMPs. So it's an amazing coincidence that it plays this triple role. But again, it's unexplained. One of the most famous coincidences was the so-called triple alpha coincidence, which was discovered by Hall in 1953. The question is, how do we make carbon? Carbon is made through a process of what's called the triple alpha process. Two alpha particles, helium nuclei, combined to form beryllium, and then the beryllium combines with another alpha particle to form carbon. But the trouble is, the beryllium would normally decay too fast before it could interact with another alpha particle. And that was a puzzle, because we know we have to make carbon for life. Hoyle pointed out that this can only work if there is a resonance in this reaction, which means that you make the carbon faster than you would think you would. And actually, Hoyle predicted that resonance, and they looked for it. And he said to his friend Willie Fowler, he said, look for the resonance, and they found the resonance. So that's an example of an anthropic prediction. This argument has been done more precisely more recently. Oppenheimer et al. Say it fine-tunes the strong interactions to 5%. Ekstrom says it fine-tunes it to 0.1%. So as I said, this might be viewed as an anthropic prediction. There are all sorts of fine-tunings that are associated with chemistry. Remember, alpha S, the strong fine coupling constant, is about 10. If we increased alpha S by 2%, all the protons would go into diprotons in the Big Bang. But in that case, there would be no hydrogen-burning stars. So, for example, they wouldn't have time for life. Hydrogen-burning main sequence time of stars is long, 10,000 million years, and that's how we get life. If you increased it by 10%, all the protons would go into nuclei of unlimited size, and then you'd have no chemistry. If alpha was decreased by 5%, all ordinary deuterons would be unbound. That's to say, the electric force would be bigger than the nuclear force, and so the only thing in the universe will be hydrogen. So again, there will be no chemistry. And this is a diagram from Tegmark, which is sort of doing that more precisely. There are other constraints which involve the masses. For example, the electron-proton mass ratio must be 10 times alpha squared in order to have chemistry. And the difference between the neutron and the proton must be something like twice the electron mass. Those are required, okay? And they're required for chemistry, but again, they're not explained, because fundamental physics still doesn't tell us what the relationship is between the mass of the electron and the mass of the proton. Nowadays, of course, we don't think so much of we don't think of the neutrons and protons as fundamental. We have to think in terms of the QCD strength in quark masses, but you have a similar diagram where you find in terms of the electron mass and the mass of the down quark and the up quark ratio, you have to be in a particular place. So it's whichever way you look at it, it requires fine-tuning. Another constant in cosmology, which is very important, is the photon to baryon ratio. The photon to baryon ratio is about 10 to the 9th. So you might say, well, why is the photon that's the number of photons per baryon averaged over the universe. So then you might ask, well, what is the why does S have that very large value? Well, there are some constraints. For example, the universe would be matter. We want the universe to be matter-dominated. You know what happens in the universe starts off radiation-dominated and then becomes matter-dominated. We want it to become matter-dominated before the Dicke time, which is the main sequence time of a star. That says that S must be less than alpha g to the minus a quarter, which is 10 to the 10th. So that's just saying if we want to have stars, S better be bigger than 10 to the 10th. On the other hand, if you want the universe to be radiation-dominated at Big Bang nucleosynthesis, you can show that S has got to be bigger than this thing, which is 10 to the 4th. If the universe was not radiation-dominated, all the universe would go into helium. And so we've got this anthropic constraint. It's not a very strong constraint, 10 to the 4th to 10 to the 10th, but at least some constraint. Well, of course, about in the 1980s, cosmologists started realizing that what S represents, it represents the baryon asymmetry between matter and antimatter when you go before 10 to the minus 5 seconds, when you pair produce matter and protons and antiprotons. And then the idea was that the baryosynthesis, that this asymmetry is associated with baryon violating processes at the gut epoch. So you might say, well, this is irrelevant. That's an anthropic argument. And with time, some anthropic arguments do go away. New ones come and some go away. But you see, it's not as simple as that, because in these baryosynthesis models, the photon to baryon ratio is basically some power of alpha x, which is the sort of grand unified coupling constant. But if that's less than alpha g to the minus a quarter, that's saying that alpha g must be less than alpha to the 4 to the power n. N is some integer. So if n was 5, for example, that gives you exactly the same as the convective star condition. So actually, just saying S results from baryosynthesis itself merely draws attention to a fine-tuning as well. There are lots of other numbers that Rees refers to. And many of these we've talked about. There's the strength of the nuclear binding energy, the matter density of the universe in critical density, cosmological constant, the size of fluctuations, the number of spatial dimensions. Oh. And what about constraints on the dark matter density? Well, omega can't be too large, because if it did, the universe would recollapse too soon. That's very overdense. It recollapses before galaxies can form. On the other hand, if omega was much less than 1, that means that fluctuations stop growing at a certain time, and they'll stop growing before galaxies can form. I'm giving you actually the original arguments as presented in my paper with Martin Rees, and sort of showing how, to what extent they still apply. So at that stage, one could sort of say omega is between 0.1 and 10. Not a very strong constraint. But then, of course, since then, we had inflation, which came actually a few years after our paper. Inflation, of course, is supposed to tell us that omega is 1. So you might say, well, there's no longer any need to have an anthropic constraint. But actually, that's not true either, because inflation also requires a lot of fine-tuning, which can be interpreted. Now, I have a little slide on inflation here, which I think I'm going to have to miss out, because inflation is very much tied up with the multiverse. So you've got to ask yourself, do you believe in inflation? Most cosmologists do, but not everybody. And I take what I think is a balanced view of inflation. I take the view, you see, there's so many models of inflation. It's really not it's not really a model. It's more like an effect, an inflationary effect, just saying there was a cosmological constant. It makes a lot of robust predictions, which I'm sure you all know about, but like scale invariance and fluctuations and Gaussianity, etc. But then lots of other models also have those predictions. So I would say the evidence is sort of circumstantial. But there's so many things inflation must do. It has to start, it has to last long enough, it's got to end in the right way, it's got to leave the right density fluctuations. So you've got to ask, is it natural? You've got to ask actually what is the inflaton, because remember we don't have any evidence for any scalar field in nature yet, apart from the Higgs particle, I guess. And the other problem is that you have to have at least 70 e-folds of expansion, and that means that your horizon, that means the sub-horizon scales today must originally have been sub-Planckian. So there are problems with inflation, and I'm going to skip the next slide because I'm running out of time. But the basic message of the next slide is that inflation requires fine-tuning. So you can't just assume that inflation solves everything and it explains why omega is 1, because inflation itself to work requires a lot of fine-tuning. And that itself might have anthropic significance. Another of these quantities was the amplitude of the fluctuations required to make galaxies. We know what that amplitude is. It's something like Q, it's something like 10 to the minus 5. That's the amplitude of the horizon epoch. And we know that Q can't be too small, because if it was, gas can't collapse into gravitationally bound structures. On the other hand, if it was too big, bigger than 10 to the minus 3, regions would collapse the black holes. And so you get quite complicated diagrams like this, which tell us that we can actually only exist. This is a parameter space of Q against matter density per photon, but we're only in that little white region, so we need fine-tuning there to get, we need to basically have Q as something like 10 to the minus 5. And then maybe the most famous constant of all, is the cosmological constant. And I'm sure you all know the argument here that the actual, we now know, we think there's a cosmological constant from the acceleration of the universe, but the most natural value of the vacuum density is the Planck density, which is smaller by a factor of basically 112. And so, 120. And so there's this incredible fine-tuning in the cosmological constant, which is still not explained. And the person who first drew attention to this as an anthropic coincidence was Weinberg. And Weinberg pointed out that if omega was too large, galaxies would never form, because the point about the cosmological constant, it stops density fluctuations growing at a certain time. And he pointed out that if omega lambda had better be less than 0.6 in units of the critical density, otherwise you can't actually make galaxies. So he said, let's imagine physics produces all possible values for the cosmological constant between basically minus 10 to the minus 120 and plus 10 to the 120, which is just the Planck density. Then you simply say that for galaxies to form, we have to be in a region where lambda is sufficiently small. And that's an argument which has swayed a lot of people. That's why people like Weinberg actually got interested in the anthropic principle. He is now one of the proponents of it. And in fact, for example, what you can do is you can take lambda and Q. Q is the amplitude of the fluctuations, and lambda is the cosmological constant. And you can say in this diagram exactly where we have to be. We actually are in this region here, because that's the only way we can have galaxies and also have not so large cosmological constant that it actually stops galaxies forming. Well, I've now gone through all of the this is a diagram finally about the number of space and time dimensions. We know we live in a three spatial dimensions and one time dimension, but in particle physics you can have models with different numbers of space and time dimensions. This is a diagram from Tegmark explaining what goes wrong with all these other dimensionalities. So you could even argue that the dimensionality of space and time has got anthropic significance. I wouldn't say this is a strong argument, because there might be many other, there could be particle physics reasons for believing that we live in 3 dimensions 3 spatial dimensions and 1 time dimension. But remember that M theory does predict all these extra dimensions, and it does become an issue to understand why we live in a universe of 3 plus 1. Now, so how many then tunings are there? And I've just summarized here. Most of these tunings are associated with a particular time in the history of the universe. So I've gone through most of these. I won't go through them again. This is basically a summary of all the fine tunings I've talked about. So when you say how many, well, there are quite a lot of them. I think there's enough to think, there's a real problem there. Roger, when did I start again?
You've got about 1 minute.
But that's excluding question time, is it?
Yeah, we've got there's still 8 minutes before the next talk. So
okay.
If we leave 1 or 2
in a
minutes
way, can we have discussion right at the end? Is there time for discussion at the end of the day, or does it have to be after the individual talk?
I think it's best to have some discussion after this talk.
Okay.
If you can possibly give us a few minutes.
Okay. Now, so anyway, the view of physicists has been very varied to the anthropic principle. Freeman Dyson, I do not feel like an alien in this universe. The more I examine the universe and examine the details of its architecture, the more evidence I find that the universe in some sense must have known we were coming. So he was a great believer. On the other hand, here is Padgels. The influence of the anthropic principle on contemporary cosmological models has been sterile. It has explained nothing, and it has even had a negative influence. I would opt for rejecting the anthropic principle as needless clutter in the conceptual repertoire of science. And some people still take that view. But the middle way comes from Carter, who coined the word. The anthropic principle is a middle ground between the primitive anthropocentrism of the pre-Copernican age and the equally unjustifiable antithesis that no place or time in the universe can be privileged in any way. And I would say now, with the popularity of the multiverse scenario, quite a lot of people go to agree with Carter. The question of whether this makes the multiverse proper science is obviously something George is going to, I imagine, address later. Now, I should just end with the objections to the anthropic principle. I mean, I guess I am, after 40 years, an advocate of the anthropic principle, but I try and be balanced. So let me give you some of the objections. You could just say it's all a coincidence. That, as I said, depends on how many tunings there are and how precise they are. I would just refer you to 2 papers. Victor Stenger, The Fallacy of Fine-Tuning, Why the Universe is Not Designed for Life, and Luke Barnes, The Fine-Tuning of the Universe for Intelligent Life, which take very different views. I side with Barnes. One complaint can be that these tunings are mainly post hoc. But actually, there are triple alpha was a prediction, and in some sense, lambda was a prediction, because Weinberg actually, I should have said, Weinberg predicted the value of lambda before it was actually discovered through the cosmic acceleration. Obviously, you might say that it's too anthropocentric. Well, it's nothing to do with men and women, okay, I've said that, but on the other hand, it does assume carbon-based life, and it assumes planets and stars and things. As I said before, I think the fine-tuning should be associated with complexity. Not even life, to me, is, I think, too general. I think of it as being associated with complexity. Complex structures, because all those things around the Ouroboros are examples of complex structures. The other thing is that it doesn't explain exact values. Whatever the fine-tuning, it doesn't tell you that alpha has to be exactly 1 over 137. It's just saying it has to be within some bounds. Now, if you adopt a multiverse picture, that's fairly natural, because you're just saying, all these multiverses have different values for the constants, and we just happen to be one where it's in the right range. But it doesn't predict exact values. That's true. Some people say, well, the final theory may predict, there might be a final theory which will predict the constants uniquely. That was the dream of most physicists originally. But even if that was true, it would still be a remarkable coincidence, a sort of meta-coincidence, that the values predicted by the final theory were just what was required to make life. So I don't think that really solves it. And the other objection, of course, a somewhat different type of objection, is that it's all too philosophical. It's not science as we normally know it, and that is undoubtedly true. Now, you know, I sort of take the view, I think when Martin Rees and myself wrote our paper, we sort of said, well, there is something to be explained here, and any explanation is better than none, whether you call it science or not, is one can argue about. I've had my own disagreement with George about whether the multiverse counts as philosophy or cosmology. And I have my own compromise, which I don't know if George is happy with, but I take the view that the whole history of cosmology, the boundary is there's always a boundary between philosophy and science when you look at the largest and smallest scales. And in particular, the whole history of cosmology has been one in which, at the frontiers of cosmological knowledge, it's always been the case that the more conservative skeptics are saying, this isn't science, this is just philosophy, or even theology. But actually, so I regard cosmology as evolving, because the ideas on this border of cosmology and philosophy, I call it metacosmology. But the metacosmology becomes proper cosmology when data accumulates. So I call the multiverse metacosmology because we don't yet have the data for it. We don't have the empirical evidence. If the empirical evidence comes, we'll call it cosmology. Until then, it's metacosmology. And so metacosmology represents a sort of purgatory, okay, before you know where you're going to go. And the whole history of cosmology is metacosmology becoming cosmology. Now, I'm going to cut
Probably
this.
should wrap up
I've got to wrap up. So there's a whole question of what counts as an observer and what is selected for. This is my picture of the pyramid of complexity, just to say why I focus on complexity. The point is that as you go from the Big Bang, you get a sequence of, you have quarks forming nuclei form atoms, atoms form molecules, etc. All of this only happens because there are these fine tunings. So to me, the purpose of the fine tunings is that it does actually generate this pyramid of complexity. And of course, it may be right at the top, the most complex things we know about are our brains and consciousness. But that, to me, it may even be incidental, because once we've got life forming on the planet, it seems to me very soon you end up with, you may end up just forming consciousness, almost routinely. So to me, the first step is the difficult one, forming molecules. So to me, that's why I think of it as the complexity principle. And one doesn't need to get too bogged down with the question of what precisely do we mean by, what precisely is it which is producing the selection effect. Okay, so I've got to finish now. Roger, let me see if there's a final. I had far more. So these are the three models which I started with. I gave right at the beginning of the. I'll just do my little diagram there. These were the three. How come? I've left how come to negative time, but basically, there were the three explanations. The multiverse, I would think of that as physics. Saying consciousness, I call that metaphysics. God, I would call theology. But people do disagree about these boundaries. Some people, for example, think that the multiverse is metaphysics and consciousness is theology. And then you'd want to produce something like, this is the Stephen Hawking, the universe is a nutshell, where there's only one universe which sort of creates itself. So there is a Boggle threshold, and I'll just say that I'll end up here on this slide because it leads to George rather naturally. These ideas, I call this metacosmology, as I said. So ideas like the multiverse to me are metacosmology, but they can become cosmology once we have evidence for these other universes. So this is what the significance of that red arrow is. And I'm not going to get into theology at all, but George is interested in theology, and I call that cosmology with a really big C, I suppose. Cosmology with a C. But I think actually I'll stop at that point. Sorry to go on a little bit long.